In this video, I intend to teach you absolutely nothing. Thanks for coming to my TED Talk. No, wait, we'll just be connecting a bunch of dots together. The dots that we want to connect together is using a combination of pre-calculus and calculus to sketch the graphs of functions. So, combination of things from pre-calc and calc that we're going to be doing. So, the task at hand is simply going to be, here is a function. Sketch the graph in its entirety, including all of the necessary details. So with that in mind, we will start with the domain of a function. Now, domain will let you know on what values of x is this thing actually defined. So more than that, we got to be looking for domain issues. So things like denominators, or even indexed radicals. Or things like logarithms. All of these things have built-in domain issues that are discussed in pre-calculus. Inverse trig functions as well, though those tend to not come up nearly as frequently. Second thing to look for would be intercepts, also from pre-calculus. So if the given function is y equals f of x, two different kinds of intercepts that we can find. A y-intercept is simply going to be find f of 0 if it's in the domain of the function. And for x-intercept, this is where we would set f of x equal to 0 and solve for x. Third thing we're going to look for from pre-calculus is whether or not this thing has any sort of symmetry. So again, we'll use the moniker of f of x for this. If f of negative x happens to be equal to f of x, that means that opposite x values produce the same y value. This would be an example of y-axis symmetry. Y-axis symmetry, and we refer to that kind of function as an even function. If you take f of negative x and you wind up getting negative f of x, then what you have is referred to as origin symmetry, which is referred to as an odd function. Now, if you evaluate f of negative x and you get neither the original function nor the negative of the original function, then you don't need to worry about any sort of symmetry and you can proceed as is typical. Next up, something to look for with trigonometric functions is periodicity. Periodicity, a periodic function is something that repeats itself every so often, such as a sine function or a cosine function. So this will apply to trigonometric functions only. Now, unless there is something else given in the problem, a typical period for a trigonometric function is going to be 2 pi, though there are some special situations where that doesn't necessarily have to be the case. For number 5, this is where we're going to start blurring the line between pre-calc and calc, because we learned about these things in pre-calc, but we were more specific about things in calculus, and that is the idea of asymptotes. Now, 3 different kinds of asymptotes exist. We'll be looking specifically for 2 of them through the use of calculus. If we take the limit as x approaches a, or as x approaches a from the right, or as x approaches a from the left of f of x, and we wind up getting plus or minus infinity. Typically, we only look at this around domain issues or endpoints for a domain. This is a vertical asymptote at x equals a. Now, if we take the limit as x approaches plus or minus infinity of f of x and we wind up getting a value for that, this would be a horizontal asymptote. and that'll be at y is equal to L. Now it is possible that a function can have two different horizontal asymptotes, like in the case of the arctangent function, so it will be important for you to go to positive infinity and to negative infinity. This applies to inverse trig functions, exponential functions, those are the big ones. Next, we start getting into the exclusive calculus stuff. So we started off chapter 4 talking about intervals of increase and decrease, as well as critical points. Critical points and intervals of increase versus decrease. This is where we took a derivative, set it equal to 0, solved for x, and then used those things to try to figure out where this thing was increasing and decreasing. All of this started with a derivative. So if you solve the equation, f prime of x is equal to 0, you can find all of the critical values of a function, and then we'll make a little note, or f prime of x does not exist. Those are the two possibilities for a critical value. Critical values break up our domain into test intervals, and then we're going to check to see on each interval whether this thing is going to be positive or negative. So if the first derivative is positive, you have yourself an interval of increase. And if f prime of x is negative, you have yourself an interval of decrease. One thing that intervals of increase and decrease can do for you is allow you to classify critical points as being either local maxima or local minima. As far as local maxima and local minima are concerned, you have two different options for identifying something as a local maximum or a local minimum. Those two things we have are the first derivative test and the second derivative test. So first derivative test says look to the left of a critical point and look to the right of a critical point. Does the function change from increasing to decreasing? That is, f prime of x is greater than 0, followed by f prime of x is less than 0. Or does it change from decreasing to increasing? That is, f prime of x is less than 0 changes to f prime of x is greater than 0. The first derivative test allows you to conclude that the first situation is a local maximum, and the second situation is a local minimum. The second derivative test says, suppose you're at a critical point. We'll just assume for a moment that f prime of c is equal to 0. If f double prime of c is less than 0, then the function is concave down at that point. In order to be concave down, we would have to curve our fingers in such a way that our palm faces down. That would be exactly the situation of a local maximum. However, if f double prime of c is greater than 0 at that point, then you have yourself a local minimum. This, of course, lends itself very nicely to point number 8, which would be the inflection points. And intervals of concavity. So number 8 is basically do what we just did with number 6, but do it with a second derivative. If a second derivative is equal to 0, and you're able to show that the concavity actually changes from positive to negative or negative to positive, that is typically what we look for in terms of an inflection point. On intervals where f double prime of x is greater than 0 This is where we can see a function to be concave up. And if it is less than 0, that's where we can count on something being concave down. Now, associated with all of these critical points, points of inflection, all of these things, it is going to be important for you to also figure out the corresponding y value for all of these. So an important clarification that needs to come up is, what are we actually finding when we plug these things into either a function or its first derivative or its second derivative? If you plug it into f, you're finding a y value. If you plug it into f prime, you're finding whether this thing is increasing or decreasing. And when you plug it into f double prime, you're checking for its concavity, whether it's concave up or concave down. So, this is a rather long process, and the problems that we're going to see are going to be awfully long, but you can always skip forward to step 10 if you need to. Step 10, as coined by my previous Calc 1 class, is cry. We'll only step 10 a little bit this semester. We'll be fine.